Okay, so this video covers the whole of the FC22 booklet, which is percentage yield and atom economy. And this is in fact part of the molar calculation section of the syllabus. So it's in 2.1.3 amount of substances at the end of that section of the syllabus here. So it's a very, very brief section and it shouldn't take very long. So what you need to do for this topic is to work through the calculations in the classwork booklet on percentage yield and atom economy, and then learn some factors that affect percentage yield and also why high atom economy is desirable in industry. And these two relate to the idea of sustainability, the idea that the raw materials you need to use are in limited supply, and also that you don't want to produce waste products because you need to then deal with the waste products, whether they are toxic or whether they're harmless. You still need to dispose of them or store them, and there's a cost associated with disposing or storing those waste products. Percentage yield is a value that tells us how much product we actually get compared to what we should get if all the reactants convert to products in a reaction. So for example, I have a reactant here in a reaction, and we're going to convert this reactant to a product here. And in this case, I'm hydrolyzing this haloalkane, this bromoalkane, using an alkali. Now, using the stoichiometry, I can work out exactly how much alcohol I should get if I know how much bromoethane I have at the start. If all the bromoethane converts to the alcohol, which will be 100% yield, if I started with 0.1 mole of the bromoethane, I should make 0.1 mole of the ethanol because the stoichiometry is 1:1. Now, if I only get 0.05 moles of ethanol at the end for whatever reason, and there's a number of different reasons we come to later to explain why we don't get 100% yield, we will get, in this case, 0.05 divided by the expected theoretical maximum, which is 0.1, and that will be a 50% yield. You can get a percentage yield anything between 0 and 100% yield, but you should not be able to get more than 100% yield. If you've got more than 100% yield, you made a mistake somewhere in your calculation, or you may have measured something wrong in your practical. One of the reasons why some people get the calculation wrong is that they haven't thought about the fact that some of the reactants may be limiting factors. So you've got to be aware of limiting factors when you do these calculations on percentage yield. So for example, if I have a reaction where I have 0.5 moles of sulfuric acid added to 0.5 moles of sodium hydroxide, there's actually a limiting factor in this reaction because the stoichiometry is 1:2 for the acid to alkali. So if I've got 0.5 moles of the acid, I would actually need double that in terms of the alkali. So I would actually need 1.0 moles of the alkali. Now, I've only got 0.5 mole, so there isn't enough of the alkali to react with all the acid. So this is the limiting factor in this scenario here, in this reaction here. And this will limit how much the product I will get, how much of the sodium sulfate I'm going to get, because not all the sulfuric acid is going to give me the sodium sulfate. So I'm not going to get 0.5 moles of sodium sulfate, even though the stoichiometry of the sulfuric acid to sodium sulfate is 1:1, because the sodium hydroxide is limiting how much of the sodium sulfate I'm going to get. This is the limiting factor. So the actual amount of sodium sulfate I'm going to get isn't 0.5, it's going to be limited by the amount of sodium hydroxide, so therefore the amount of sodium sulfate I'm going to get at the end is going to be 0.25 moles. So this will be my theoretical maximum in my equation for percentage yield, because this is the maximum amount of sodium sulfate I can get if I use these amounts of the reactants here. There's no way I can get any more of the sodium sulfate. So you need to be aware of the limiting factor in working out percentage yield. So why is it that we don't get 100% yield always? Why is it unlikely that we're going to get all the reactants converting to the products all the time? Well, we're going to look at some of those factors. So one of the reasons is that often we try to purify the product away from the byproduct. So for example, in the previous reactions, we had more than one product in the equation, and we need to remove the desired product away from that mixture, whether it's through distillation or it could be filtering a precipitate produced, for example. And those purification steps can often lead to product being lost. So you may leave some product in the filter paper, or you may find that not all the product's been distilled away from the mixture and so on. And crystallizing is a purification method we're going to look at in the second year, so don't worry about this too much now. And you can also get product being lost if you transfer from one vessel to another. So if you're using a separating funnel and you separate out your desired product, you may leave some of the desired product in the separating funnel, or you may leave some in the beaker from pouring into the separating funnel. So you can leave things behind in transferring between reaction vessels like beakers and conical flasks and so on. Another reason for a reaction not having 100% yield would be the fact that the reaction is reversible, something like the Haber process or esterification when we do that in the second year. And not all the reactants then will convert to products, because some of the reactants will convert back to the reactants. So we have a lower than 100% yield then. That will only apply to reactions which are reversible, obviously. So it won't apply to something like combustion, for example. You burn a piece of paper, it's not going to revert back to the paper from the carbon dioxide and the soot and smoke. Even if the reaction is not reversible, the reaction could be quite slow, and if you add the reactants together and only wait a short period of time, you may not get enough of the products produced, and therefore you find that the yield actually quite low. And if you waited longer, then the yield would probably increase a bit more. The last reason that you may not get 100% yield for a particular reaction, we've seen before in a previous topic, and that is the fact that you may get side reactions. And we looked at this when we looked at reactions involving radicals, where you've got many different side reactions that could occur. So those side reactions means that you use up the reactants to produce other things other than your desired product. So therefore, the percentage of desired product is going to be low. So reactions that can produce lots of different other products or byproducts will generally have lower percentage yields. So we've looked at percentage yield and how to calculate percentage yield. And when we calculate percentage yield, we need to consider whether there's any limiting factors in the reaction we're looking at. We also looked at the factors that may affect percentage yield. So what we're going to do next is to look at atom economy and how to calculate atom economy and why we need high atom economy in industry. And these two relate to sustainability. The percentage atom economy of a reaction is an intrinsic value of the reaction and doesn't depend on whether the reaction is reversible or not. It doesn't depend whether you purify the products and you get loss of products through transfer of vessels and so on. So it only depends on the relative formula masses of the reactants and products. In fact, it only depends on the relative formula mass of the desired product compared to the relative formula mass of all the products or even all the reactants, because according to conservation of mass, the sum of the MR of the products will equal to the sum of the MR of the reactants. So it doesn't matter if I use the sum of the MR of the products or the sum of the MR of the reactants, it's the same number. The percentage atom economy of a reaction tells us how much waste there would be for a reaction, even if there's 100% yield in performing the reaction. The higher the atom economy of a reaction, the less waste there is for the reaction. And if you've got 100% of the atom economy, then there'd be no waste at all for that reaction. So it's better for us to choose reactions with high atom economy if there's a choice of reactions to make a desired product. So in this example of preparing ethanol, there's a number of different reactions that can make ethanol. For example, you can use fermentation from sugar, you can use hydration of alkenes as we've got here, or you can hydrolyze a halalkane as you've got here. And these reactions may have different atom economies, and in these two cases we got quite different atom economies. So in this example, if I hydrolyze bromoethane to make ethanol, the atom economy is only 30.9% because it's calculated from the relative formula mass of the desired product. In this case, I've chosen ethanol, divided by the relative formula mass of all the reactants or all the products, and it doesn't matter which one I choose because the sum of this is the same as the sum of this. In this case, we get 30.9% atom economy because there's a byproduct here with a very large relative formula mass. Bromine has quite a large relative atomic mass, so contributes to quite a bit of mass of the byproduct. In the second way of making ethanol, we can see there's only one product, so there's no byproduct at all. If they do react, the atoms in the reactants will convert completely to the products. None of the atoms in the reactants will make a waste product. So for any addition reactions, we always get 100% atom economy. However, don't confuse 100% atom economy with 100% yield. You could have a reaction with 100% atom economy like this one here, but the reaction may be reversible. So not all the reactant particles may convert to products, and some of them may revert back to the reactants. And therefore we get lower than 100% yield because we're not getting the maximum number of moles of products produced as not all the reactant moles are converted to the products. Choosing a reaction to produce a desired product with a higher atom economy will be better for sustainability, as it reduces the amount of limited resources we need in terms of the reactants we need to use. So for example, using a smaller mass needed to make a same amount of product, we will use less fuel to transport that raw material from one place to another. Higher atom economy will also mean that less of the reactant mass will be converted to waste, so we will reduce the production of waste, and whether this waste is toxic or not, we still need to somehow get rid of it or store it. So there'll be a cost involved in transporting that waste to a disposal site or to a storage site. However, we can't just look at atom economy on its own in terms of choosing a reaction in industry, because there's lots of different factors that we need to consider, and one of the main factors is cost. So if a reaction has a high atom economy but requires very expensive equipment, which is a fixed cost, or takes a lot of energy to run, which is a variable cost, then that may not be a suitable reaction for the company to choose. Also, if you've got a high atom economy, let's say 100% atom economy, but the percentage yield is very, very low, then that may not be suitable as well. So you've got to think about the pros and cons of each factor in order to choose a reaction to produce a desired product in industry. So we come to the end of this video for percentage yield and atom economy, and we just looked at how to calculate atom economy. We also looked at why it's desirable to have high atom economy in industrial processes to reduce the waste that's produced, as any waste produced will have some sort of impact to either the environment or cost of disposal. Sometimes you may have a reaction where the byproduct produced is safe to release to the environment and there's no cost involved in that disposal. So for example, you have a byproduct which is a safe gas to release into the air. There's no cost involved in releasing it into the air and there's no negative impact on the environment. However, not all reactions are like that, so we need to consider lots of different factors that affect maybe the yield and the atom economy and the economic and environmental costs in producing the product. So that relates to the idea of sustainability.